In the first example, we are talking about the volume of a spherical balloon that is increasing at a certain rate. So let's write the volume of a spherical balloon is increasing at a rate of 100 cubic centimeters per second. So this is pretty much the data. There is only one piece of information that is required. The question that we need to answer is the following. How fast is the balloon's radius increasing when its diameter is 50 centimeter long. Okay? So let's see if we can understand what's given to us here, and what is it that we need to find. Okay, so how we translate this problem. First of all, we need to recall the volume of a sphere. Okay, volume of a sphere, some of you may know that, and some of you may not remember it. V as a function of the radius. Anybody recall what is the volume of a sphere? 4/3 pi r cubed. Very good. Okay, r cubed will give you the 3 dimension. If r is measured in centimeter, then r cubed will give you cubic centimeters. So this is given. So what's given to us actually? We know that the volume of the spherical balloon is increasing at a rate. So we have the rate, and this will be dV, but the rate is in cubic centimeter per second. So this is actually going to be dV dt. And dV dt is 100 cubic centimeter per second. The other thing that we know is that D equals 50 centimeter, or R equals half of it, or 25 centimeters. So these are the two items that are given to us. What we need to find is how fast is the radius increasing. So it will be dr dt. That will be how fast the radius is increasing. Okay, so now you can think, maybe we simplify the problem a little bit. So we're going to look at dV dt, but we have v as a function of r. So we need to apply the chain rule. And we're going to say the following. We're going to say that dV dt, which we know, equals dV dr, which we can find out, times dr dt, which we need to find. Okay. And this is the heart of the solution. Once you recognize that you have basically a composition, V of t is V of r times r of t, then you can apply the chain rule. So note, V of t is the composition V of t equals V composition R of t, okay, or V of R of t, like so. And If you have a composition, then the derivative is the chain rule. Okay, so what is the VDR? If V of R equals 4 over 3 pi R cubed, then dVdr equals what? 4 over 3 pi is a constant, so it will be really the derivative of R cubed, which is 3R squared. And if you reduce it, you have 4 pi R squared, which has some significance. What the heck is 4 pi R squared? All right, I need to reveal it to you then. I'm sorry? It's the surface area. It's the surface area. And this is a remarkable result. We have the volume. We take the derivative of the volume with respect to the radius. So we start with the volume. We end up having an area because R squared is a two-dimensional quantity. And the relation between the volume and the surface area is such that one is the derivative of the other. Another example, what is the area of a circle? You all know that. Pi r squared. What is the derivative of pi r squared? Come on, give it to me. 2 pi r. What is 2 pi r in a circle? It's the circumference. Again, think about it. The area of a circle is pi r squared. The derivative of a circle is 2 pi r. The derivative is the circumference. It's remarkable how the designer of calculus find out, whether intentionally or not, that the relationship between the volume and the surface area and the relationship between the area and the circumference. This is one of, I don't know how to describe it, but the first time I realized that as a young kid, I was like awestruck. I mean, who designed the universe such that it will fit so nicely calculus? Of course, it's the other way around. What you're trying to do with calculus and any other science is to understand the universe. But it's such a nice fit in this case that it's a remarkable result. All right. I'm sorry? Let's go on now, apply the chain rule. dV dt is something we know, it's 100, right? And 100 equals 4 pi r squared. Well, actually, I need to replace r with 25, so 4 pi r squared dr dt when r equals 25. Okay, so we end up having dV dt equals 100 divided by 4 times pi times 25 squared. Okay, and here we have a quick simplification. 25 times 4 is 100, so we end up having 100 times 25. So we have 100 divided by 2500 pi, or 1 over 25 pi, and the unit will be, so this is dr dt centimeter per second, like so. Now, if you want to calculate it, be my guest, but I'm happy with this result. And I think I'm going to go ahead and, well, I have time to move on. So.